Hello everyone, this is Shaahin. I'm an assistant professor in the Department of Electrical and Computer Engineering at the New Jersey Institute of Technology, and today I'll be presenting our work titled Integrated Sensing and Computing Using Energy-Efficient Magnetic Synapses at ISQED Symposium 2022. I received my PhD in electrical engineering from Arizona State University in 2021, and here I listed ACAD Lab Advanced Circuit to Architecture Design Laboratory Research Directions. We are mainly working on accelerator design for big data applications, deep learning, bioinformatic graph processing, in-memory computing with volatile and non-volatile memories, and adaptive learning for collaborative in-edge AI computing IoT systems. Here is the outline of our two-day talk. First, I present you the motivation behind our research by talking about power wall and the memory wall challenges, and then I will talk about the Spintronic devices that we use to realize our integrated sensing and processing platform. Then we will talk about the domain wall motion device as a multi-level weighted storage. Then we will have the integrated sensing and computing platform, circuit and architecture. At the end, we will go to the evaluation part, and then we have a conclusion. Now let's talk about the big data computation challenges. As we are moving towards big data processing, current computing platforms have faced different challenges from device and architecture perspective, so-called power wall and memory wall. Low power design is considered to be one of the greatest challenges in semiconductor industry, especially for mobile and IoT devices. Here on the left figure, I'm showing you the mobile SoC power roadmap for ITRS. And we can see that since 2011, we've not been able to meet 1 watt power constraint required by mobile devices, and it is expected that by 2024, 2 years from now, 8 watt power constraint will be also violated. In the meantime, voltage scaling has slowed down, and so performance improvement in terms of frequency has considerably slowed down. One possible solution is to exploit new post-CMOS technologies like Spintronic devices or carbon nanotube field effect transistor to somehow alleviate the power wall problem. On the other side, from the architectural level, current computing platforms are based on von Neumann computing architecture with separate memory and processing units, as you can see on the right figure, that impose energy-hungry data transfer, long memory access latency, and limited memory bandwidth. One solution to solve this challenge is to move the computation unit close to where data resides, which is called processing in memory. These new platforms offer parallel local data processing, ultra low power, and also short memory access latency, and can be programmable at a low cost. In this slide, we will talk about Cloudcentric versus Thingcentric IoT devices. I think everyone knows about the impact of AI on our today's lives. As you know, deep neural networks are currently the foundation for many modern artificial intelligence applications. Actually, as you can see in the news, with the breakthrough application of deep neural networks, from object detection to speech recognition and image recognition, the number of applications that use deep neural networks has exploded. For example, self-driving cars, detecting cancers, all the way to playing complex games. In many of these domains, deep neural networks are now able to exceed human accuracy. This superior accuracy of deep neural network, as you know, comes from their ability to extract high-level features from raw sensory data. However, this data is redundant and unstructured, and it turns out that data conversion and transmission of large raw information to a back-end processor impose high energy consumption, high latency, and memory bottleneck in the structure, in the architecture that is so-called cloud-centric. To overcome these issues, computing architecture will need to shift from this approach, cloud-centric approach, to a Thingcentric or data-centric approach where the IoT node processes the sense data internally and somehow can accelerate the whole process. But what are the spintronic devices? Spintronic devices utilize the spin of an electron as a state variable for computation. In this way, spin-up and spin-down magnetization configurations can be mapped to binary 1 and 0, as you can see on the right figure. But how to control the magnetization? One way is to apply the external magnetic field. The other way, the more energy efficient way, is to exploit a spin transfer torque or a steady effect. Such a device is expected to bring ultra-low switching energy, non-volatility, excellent retention time, high integration density, and of course, compatibility with CMOS technology. Okay, now let's move on to the next part, which is domain wall motion device as a multi-level weight storage. In this work, we use the Spintronic domain wall motion device as a non-volatile multi-level resistive paradigm for weight storage in deep neural networks. Domain wall motion, as you can see here, is a four-terminal device structure consisting of a magnetic domain wall strip and a magnetic tunnel junction. A typical magnetic tunnel junction consists of two ferromagnetic layers with a tunneling barrier sandwiched between them. One of the magnetic layers is fixed, while the other one is a free layer. Due to the TMR effect, the resistance of MTJ is low when the magnetization of two ferromagnetic layers are parallel or vice versa. The domain wall motion, as you can see here, can be defined as a transition region between two opposite magnetic domains in this device. To write a weight value in the domain wall motion device, we can use the lateral terminals of domain wall motion device, here terminal 1 and terminal 2, and by applying a right voltage, the current flows through the domain wall strip, and the spin transfer torque is applied to the magnetic moments around the domain wall region. Such a steady can actually move the domain wall along the direction of electron flow in the domain wall. So as you can see in the micromagnetic simulations here that we ran using the simulators, we could get a good match with the experimental results reported in the literature. At the circuit level, the read path of domain wall motion device is modeled with three parallel magnetic tunnel junctions or three resistors, which is shown here, with variable conductance depending on domain wall positions. As you can see here, equations 1 to 3 can show that each parameter, the left, middle, and right resistors, the values basically that they can get. Now we propose a high performance and energy efficient integrated sensing and computing platform, as you can see on the left figure, to accelerate deep neural networks on the edge devices. The general architecture consists of a conventional CMOS pixel unit in vision sensors that are upgraded to a pixel, a new pixel that we call it a compute pixel, or we show it with CP. And it can work in two modes, sensing or processing. As you can see in the middle figure, every compute pixel is connected to a number of domain wall motion devices as a weight storage unit. And on the right figure, I'm showing you the upgraded pixel structure connected to a domain wall motion add-on as a non-volatile memory. At the architecture level, we modified the row decoder to activate either a single row signal for sensing or all compute rows or CR signals for the processing mode. As you can see on the right, in the sensing mode, by initially setting the RSD or reset signal at T1 transistor to a high voltage, the photodiode connected to T1 transistor turns into inverse polarization. Now turning on the access transistor T3 and K1 switch at sensor IO, photodiode can actually charge the C1 capacitor to fully charged state through our split line. Now, by turning off the T1 transistor, photodiode can actually generate a photocurrent with respect to the external light intensity, which in turn leads to a voltage drop at the gate of T2 transistor. Once again, by turning on the T3 transistor, and this time by opening the K2 switch, the C2 capacitor is selected to record the voltage drop. Now the voltage values before and after image light exposure that we show it with V1 and V2 can be sensed and amplified by the sensor I/O that we have at the end of the array. Now in the processing mode, basically the capacitor, the photodiode capacitor is initialized to a fully charged state by setting the RSD to a high voltage, just like the sensing mode. Now by turning off the T1 transistor, the row controller activates the compute row signals while all the RI signals are deactivated. This will activate the entire array for a single cycle multiplication and accumulation operation. The core idea behind domain wall motion add-on is to leverage pixels photodiode voltage as a sampling voltage for the computation. And it can actually simultaneously generate current on the compute bit lines, which you can see here with the green lines. So this mechanism converts every input pixel values to a weighted current according to the domain wall motion conductance, and the summation of the currents through each compute bit line represent the MAC result that can be sent to the activation units or neurons at the end. So in this slide, we can see that how a simple perceptron or fully connected neural networks can be mapped into the proposed platform by saving the weight values that we show it here from the MVM1 to MVMV for each compute pixels. We can map the weights, and then the inputs or the activations can be applied in parallel, and it can basically pre-process the images in the sensor before sending into the next layers or the off-chip processor for further processing. Now we're going to talk about the evaluation framework and the experimental results. We developed a bottom-up evaluation framework starting from the device-level simulation using the OOMP simulator all the way to the circuit-level simulations by the Verilog 8 coding and a SPICE simulator in 180 nanometer process node all the way to the application level. The table here compares the structural and performance parameters of selective processing in sensor designs. As different designs are developed for specific domains, for a fair comparison, we estimated and normalized the power consumption when all the processing in sensor units execute the similar task of processing the first layer of a deep neural network model with 6 convolutional layers, 2 average pooling layers, and 2 fully connected layers. We can observe that our design is the only design that offers the non-volatility, and accordingly will pave a way for intermittent computing while the other designs do not. Our design and the design in 4 are only platforms offering single cycle entire array computation scheme. In terms of the frame rate, as you can see here, our design stands as the second best design, while the design in 5 can be selected as the fastest existing design in literature. However, while the design in 5 suffers from huge power consumption, our design requires power as low as the design in these 2. We analyzed the platform's utility in processing the first convolutional layer for continuous mobile vision assisting mobile CPU and compare it with the baseline sensor CPU platform. The baseline design consists of a conventional 128 by 128 image sensor and an Intel Core i7 CPU working at 3.4 GHz with 16 GB RAM, where CPU plays the main role in processing all layers after receiving the raw data from the sensor's ADC. Our design consists of a 128 by 128 compute pixel array that processes the first convolutional layer, and the remaining layers are processed by the CPU. We found that our design performs favorably against conventional CMOS image sensors by substantially reducing the data transmission energy by about 84% paired with the CPU. The assisted CPU platform also achieves 2.4 times higher computation energy efficiency on average compared to the baseline. Besides, we observed that our platform achieves about 7 times speedup in processing input frames compared with the baseline. And this brings me to the end of the presentation. Thank you for your attention, and feel free to ask me your questions.